Welcome. Welcome to the University of Leeds and welcome to Other Suns and Other Worlds with Dr. Gaitee Hussain. Let me just get my script on my screen if you don't mind. So this is our 21st annual Bolton lecture that we organize here at the School of Physics and Astronomy at the University of Leeds. And this is our first online one. So the good thing about the lockdown is that we can now actually reach out to the world and have an online lecture, and I can welcome people from all over the world indeed. I see we've got some participants from the UK, of course, the United States, Canada, India, Japan, and a whole range of other countries in Europe. So good morning, good afternoon, and good evening to all of you. My name is René Oudmaijer. I'm a professor in astrophysics here in Leeds, and behind the scenes, I've got Professor Melvin Hoare, Shawnee Sanderson, and Erin McNeill, and they work behind the scenes to make all this happening for you. We also have closed captions, so if you would like to have subtitles, try to click the CC box below, and then you will get your subtitles for the session. Just a little bit about us here in Leeds. The School of Physics and Astronomy in Leeds hosts a very large and thriving group in astrophysics. We specialize mostly in the formation of stars and planets, and are actually now expanding even into the atmospheres of exoplanets as well. So the research that Gaitee Hussain is going to talk about is quite close to our hearts. And the Bolton lecture itself is made possible by an endowment by Stephen Bolton, who was a local oil merchant here in Leeds about 100 years ago. And thanks to his bequest, we can operate 2 state-of-the-art telescopes with state-of-the-art detectors as well up here on the roof of the building. And the entire School of Physics and Astronomy is going to move to a new building next year. And we've got 2 brand new domes thanks to this bequest as well. And we can use these telescopes to train our undergraduate students in astrophysics. Okay. And our guest today, our speaker today is Dr. Gaitee Hussain, and she's the head of the science division at the European Space Agency. And that's a very important role that she has, because ESA, the space agency, they are not only building and launching satellites to study the Earth and the planets in our own solar system and even the origins of the universe, but they make sure that the science that we get out of these satellites are the best possible, and hence she's heading a big group of scientists exploiting the results from all these wonderful satellites that ESA is building and operating. Gaitee really loved astrophysics since childhood, and she's been in many places. She got her BSc degree at University College London. She went for a PhD all the way up to St Andrews in Scotland, and straight after that she already went to ESA as a research fellow. After that, she moved to America, where she worked at the Harvard-Smithsonian Center for Astrophysics, and then went to the University of St Andrews again to then work for ESO. That's not ESA. ESO stands for European Southern Observatory. And since recently, she's now working for ESA. And well, her main research that she's doing, she's leading a team studying more about the formation of stars and planets, and especially also the magnetic fields. Okay, we'd love for you to submit questions, and please use the Q&A box to submit your questions, and they will be answered at the end of the session. So thank you again, Gaitee, for giving us a talk, and I leave the floor to you. Thank you very much.
Thanks so much, René. And thank you to everyone for joining, and also to the organizers for inviting me to speak today. I was very much looking forward to meeting many of you in person, and I'm really sorry that didn't get to happen, but I understand there are other compensations, and I'm really glad that many of you from many parts of the world are here joining us today. So in my talk today, I'm going to examine what we know about the sun and what makes it such a nice star to live around, and then talk about how we use that information to understand what environments are like around other planets that we're discovering around other stars every single day. So I'm going to now, hopefully, give me 1 second. I'll share the screen. And with any luck, this will do the right thing. Hopefully that's correct. So,
perfect.
Thank you. Okay, great. So as I said, so in this talk, I'm going to be talking about how we're starting to understand the environments around other planets. And this here is just a great artist's impression of some of the new worlds that we've uncovered. And here in this slideshow, you can see, if I can turn on the pointer, the laser pointer, yeah. So here you can see that there are planets in front of lots of different kinds of stars. So here you have something that's more like our own sun, but you also are finding planets around much hotter stars that are bluer, and planets of many, many different sizes and many different distances from their host stars. Here today is a summary of where we are in terms of the numbers of other worlds that we've discovered. When I stopped being a student and started out in astronomy properly, was the year 2000. And at that stage, we knew about 16 planets orbiting around stars other than our own sun. And then every subsequent year, you can see the number of planets that we knew about increases. So this is the number of planets shown on the vertical axis. Increases hugely until we reach this year. And currently, as of this day, we know of about 4,300 other planets. So this whole field has undergone a massive revolution. And you may know that the team that discovered one of the first planets orbiting around another star won the Nobel Prize earlier this year. So you can see why they've essentially changed and created a whole field of astronomy. So in the first part of my talk, I wanted to tell you about what we know about the Sun-Earth connection, because that's kind of the connection that we use to try and understand the environments around other planets and around other stars. So the Earth itself possesses a very strong magnetic field. It's strong enough that we can detect it in many different ways. And it's almost, if you look at it, at least from a large enough distance, it appears relatively simple. There's two clear poles. There is a pole very near what we call our geographic North Pole, and another magnetic pole near the what is near our South Pole. Now, in fact, the magnetic poles are offset with respect to the geographic poles by a few degrees. So in the simplest terms, you can think of like the Earth's magnetic field as being like a magnetic field around a bar magnet, except we know that the Earth's magnetic field is not, that the Earth inside is not solid. It consists of this molten metallic core. And there's a lot of evidence from geography and geological records that indicate that the Earth's magnetic field wasn't always like this, and that over the last 71 million years, there have been almost 170 magnetic field reversals, actually over 170 magnetic field reversals. So it occasionally switches. And we think that the reason that this is happening is because the inside, the molten core of the Earth essentially creates currents. And this allows the magnetic field to essentially change over time. And in fact, if you people who study in detail actually find a lot of structure within this magnetic field. So while in the simplest possible terms, it has this very simple north-south orientation, it actually is a bit more complex than that. The other really interesting thing to point out is that the pole that's near our North Pole, our geographic North Pole, actually has a south orientation. So when you use a compass, its north needle points towards what is our geographic north, but actually it's pointing to the magnetic south currently. In a few 100,000 years, this may, of course, change. Now, this magnetic field of the Earth is really important for our survival. And the reason for that is because the sun itself is also enormously magnetic. And in fact, as I'll discuss later in my talk, while we consider the sun extremely magnetic, living near it, compared to other stars, it's a relatively weak, kind of boring star. But for us to live around it, it's still interesting. So here is an image that's been taken using space satellites on the left-hand side of this plot that's shown here. So this is the outer atmosphere of the sun at a few 100,000 degrees. Extended from it, you can see this material that's being ejected from the sun at great speeds. And this ejection, at least in this image, is heading towards us. Here is the Earth, and here is its magnetic field. If we could see its magnetic field directly, this is what it would look like. Now, the magnetic field of the Earth is kind of distorted because of the pressure exerted by solar wind and solar particles that are constantly bombarding us. When the sun has an actual storm, however, if it's directed at us, the sun can have storms and it can release a huge amount of material. These are called, when it releases material like this, it's called a coronal mass ejection. So it releases a huge amount of plasma, which is hot ionized gas heading at us. Sometimes it won't be oriented at us, but if it's oriented at us, then life becomes a little bit interesting. It could become a lot more interesting if we didn't have a magnetic field around us. But luckily, the Earth's magnetic field essentially deflects most of the material the sun chucks at us. Occasionally, some of this plasma, some of this hot ionized gas that's heading at us gets trapped within the upper atmosphere of the Earth's magnetosphere, so the Earth's magnetic bubble. So it can actually penetrate the magnetic bubble and gets trapped. And here, the Earth's magnetic field protects us because it actually channels everything to where the magnetic field lines connect back near the Earth. So they come and they channel all of this material to the poles, near the poles of the Earth. And as it channels that material, it is accelerating it, and it starts to interact with our own atmosphere. And of course, you'll be familiar with these beautiful aurorae or northern lights. And this image was taken in Scotland, where, as René said, I did my PhD. Sadly, I chose the wrong years to be in Scotland, and I never managed to see an aurora. Aurorae can even be even more stunning when seen from space. And this was taken by one of the ESA astronauts a few years ago. And now, at its best, when a solar storm hits us, that's the best thing that can happen. We also need to protect our satellites. We have many satellites orbiting the Earth, and there are more coming. And often we have to shut down sensitive functions on those satellites because these particles that are heading at the satellites can actually potentially damage them. In the past, in the distant past, we also know of some pretty spectacular storms that headed our way. In 1859, a little bit before I was born, there was a massive storm. We call it the Carrington event, that had a direct hit towards Earth. And it caused aurorae that were so bright that at night, miners woke up in America, and they thought that it was daylight. And so they started making breakfast. More seriously, at that point, the height of technology was telegraph operators. And telegraph operators actually got shocks and got burnt because there was so much charge in the atmosphere due to the effect of that storm. Luckily, since 1859, we haven't had a direct hit that is that severe. Although in 1989, a severe solar storm, a coronal mass ejection, managed to knock out power grids in Quebec. And so this is something that governments are becoming looking at a lot more seriously. In 2012, as recently as 2012, we had a near miss. If this coronal mass ejection had gone off 2 days earlier, then it would have had potentially quite serious consequences for us. But generally, we're quite lucky. And like I said, the sun can have these storms in pretty much any direction. So we have to be pretty unlucky for it to hit us directly. So going back to my original premise, the sun is actually a pretty nice star to live around. Its magnetic field affects pretty much every aspect of the sun that we see. All these pretty images that you see here on the right show different layers of the sun, all taken at different times. The first sort of first 4 images here are really based at lower down on the sun. So it's based at what we call its photosphere or its surface. And then the subsequent images go further and further out, and they represent hotter and hotter material that's, first of all, about 10,000 degrees going right up to 6 million degrees. And these were all taken at the same time. So you can see that where you have the hottest, highest temperature material further out in the solar atmosphere, it overlies very well where you have these dark sunspots at the solar surface. And this is, NASA did this beautiful patchwork image of the sun, showing how it looks in all its different layers of atmosphere. So the point I want to draw your attention to here is that its magnetic field affects every single layer that we can see of the sun, and it makes it look quite different. Now, every single one of these layers react to its magnetic field in very similar ways. Using one of our satellites that now has been around 25 years, the satellite called SOHO, you can see what the X-ray images of the sun look like. So at these temperatures, a few 100,000 degrees, what these temperatures look like spanning a period of about 20 years. And you can see that it starts off in 96 as being relatively dark and not very filled up with this bright, hot gas. And then by 2000, it becomes brilliant and almost entirely covered, and then it drops off again by 2006, and then it becomes hotter again. And what we find is that there's evidence of this sort of cyclic activity where it increases and decreases with a period of 11 years very, very regularly. What we see in the X-rays and in ultraviolet wavelengths, which really probes the very hot gas, is also seen at its surface. And humans have been looking at sunspots for many hundreds of years. We even have records going back to ancient Chinese times. This plot here shows the number of sunspots we have going back to 1750. And these were satellite images taken of the solar surface at 2 different points, and near 2000 and around 2005. And you can see here, you have a peak number of sunspots, which are sort of smattering the whole surface. And then here you have almost no spots at all. The big events that I was telling you about, the Carrington event, they happened here, here, and here. So we can predict pretty much when the sun's going to be slightly more dangerous to us than it would normally be. And it basically happens every 11 years. So let's talk about other stars and use that information that we have to understand what environments are like around other stars and around the planets that we are discovering. So here is another summary plot showing of what we know about all the planets that we found so far. Now this plot shows the mass of the planets that have been found in terms of Jupiter masses. So 1 Jupiter mass is where you'd expect to find Jupiter, and that's marked out by the position J, by the symbol J. And something called the semi-major axis, which is a measure of the distance of the planet to its host star. This is measured in what we call astronomical units. And astronomical units are the distance between the Earth and the sun. 1 astronomical unit is the distance between the Earth and the sun. So the Earth is 1 astronomical unit away from its host star, and that's found here. And you can see that most of the planets that we found lie above where Venus is and where Earth is on this plot. Which means that they're all mostly, there are some exceptions here, they're mostly planets that are more massive than the Earth. So they weigh more, and they're bigger and heavier than the Earth. And the reason for that is not because there are not planets out there that are the same mass as Earth, that are the same weight as Earth, but it's more because with our current facilities, we haven't managed to probe this region in as much detail as we like. Measurements, the further down you go, the less massive a planet that you're looking for, then the less heavy a planet you're looking for, the harder it is to find. It just becomes a lot more difficult. Now, we're also learning a lot about the stars that are hosting these planets, so the stars around which these planets are orbiting. And one of the most surprising results that has come out of these missions that are looking for planets is that the stars that host them can be really hostile. And here you can see results that were obtained from a satellite that was looking for exoplanets. It was looking for planets around other stars. And we found that these stars have huge flaring events. So they're massive energetic releases of energy caused by magnetic fields on these stars. And they're much bigger than anything that we see on the sun, even once every 11 years when it decides to get active. Now, what you see here is the brightness of a star plotted against time in days for two different stars. And here you can see that the brightness is sort of rises and falls. And the reason it's rising and falling, and particularly in this one, it's rising and falling with a period of 5 days, is because the star is rotating in 5 days. And it has spots on it. And the spots are causing the brightness of the star to rise and fall and rise and fall. Now, on top of those, you can see these sort of lines that you might think are sort of just noise or mistakes. But actually, if you zoom into them, that's what's shown here. And you see them in detail and you magnify what these lines are, you can see there's this like very fast rise. So the brightness increases really, really quickly. And then it takes a long time to fall off. And this is a really typical signature of a classic flare as we see it on the sun. Now, by looking at the brightness increase that this event has caused, and comparing that to the brightness of the star and knowing the temperature of the star that we're looking at, so knowing some basic characteristics of the star that we're looking at, we can compare the amount of energy released in these events compared to ones that we've been studying for easily 50, 60 years on the sun. And what we find is that the amount of energy released is often over 100 times more energetic than anything that we see on the sun. And that becomes very interesting because these are events that become even more potentially dangerous to us than the Carrington event I was talking about earlier. So that begs the question that how is that affecting the environments or the atmospheres of the planets that have formed around these pretty radically energetic stars that we're looking at? And there's a lot of effort that's been spent by this team, Mihara and Notsu and their collaborators. It's a team based in Japan, following up on these stars and trying to work out, like, how do these stars compare to our own sun? And what they found is that even in old stars like the sun, and the sun is 4.6 billion years old, we consider it a middle-aged star. It's kind of halfway through what we consider its lifetime, its normal lifetime. In stars that are very similar to the sun, they tend to show these massive flares every 2,000 to 3,000 years. So we're probably okay, but it's interesting to know. And certainly it's interesting for us to learn about whether the sun and the Earth are typical compared to the other stars that we're looking at. And there's some evidence that we're seeing that might suggest that maybe the sun is not quite as typical as we think. When we look at enough other stars, we can begin to make those judgments. The other thing that we found by looking at stars that have planets in huge amounts of detail over many, many years, is that they also seem to have these kind of activity cycles. So you'll remember that I told you about the sun having this activity cycle where its amount of gas, the bright X-ray emitting gas that it has, hot gas that it has covering its surface, increases every 11 years. Well, these stars seem to have similar properties. In this plot that I'm showing you, this is a star that me and my collaborators have been looking at for a number of years, using X-ray satellites as well as ground-based data. And here in red, you can see what the X-ray brightness of the star is over a number of years, starting from 2012, ending just towards the end of 2018. And the black dots show what we get from our ground-based data, looking at hotter material that's closer to the surface of the star. And this star is a lot like the sun, but it's a lot younger. It's only about 600 million years old as compared to the sun, which is, as I said, 4.6 billion years old. So it's a lot younger. It has a planet. We know it has a Jupiter-sized planet about the distance that Earth is from the sun. And what you can see, or rather when you look at this data long enough, you can convince yourself that it's also following this kind of rising and falling brightness in its X-ray brightness. And that also indicates an activity cycle similar to what we get on the sun. The difference is that you will have noticed that this cycle is very short. So this period between here and here is 2 years, and it's already risen and fallen and risen again. So the size of the length of the activity cycle, the duration of the activity cycle of this particular star is 1.5 years, whereas the sun has an activity cycle, and this is shown for the flares that we get on the sun, has a period of 11 years from 2001 to 2013, 2014. And so the activity cycle is 10 times shorter. And we found at least 4 other systems that are like this. So it shows that other stars can have activity cycles. They have these magnetic fields that rise and fall. But to this day, we still don't know exactly what sets the clock for the solar activity cycle. So looking at activity cycles on other stars, stars that also have planets around them, we can begin to understand what might be setting that clock. And for the sun, we still have missions that are flying now, that are just starting work right now, that are going to be looking at specific mechanisms that we think that set the duration of that 11-year cycle. Now, this data, just to show you how we actually make our observations and where we get them from, this data is a combination, as I said, of X-ray data that we obtained from the European Space Agency's XMM Newton satellite, which looks basically with X-ray eyes at the universe, and also the ESO telescope, where I also spent some of my career in Chile, in the Southern Hemisphere. And here you can see the guanacos, which are the local wildlife in Chile, which is very, very cute. And it's very fun on observing ones. So I spent many nights observing at this telescope, at the 3.6 meter telescope, and combining that with space-based data. And it's, you learn so much more by combining different ways of looking at the same targets. So what we can also do with the data that we obtained from this telescope shown here in Chile is we can look at the star itself in a huge amount of detail, an amount of detail that begins to approach the kind of detail we get for the sun. Now, every star has a special spectral fingerprint. So you know light is made up of, the light that we get from stars is made up of many colors or frequencies or wavelengths. And you can split it in the simplest terms using a prism, where you can create this rainbow of light. If you split it up more sensitively, then you actually find that there are these dark bands in light that you get from stars. And these dark bands are unique for a star of a certain temperature. So this is a spectrum of the sun. These are all, this is the full range of light split up and stacked up on top of each other. So this is the redder wavelengths, and these are the bluer wavelengths, or the higher frequencies, and the the lower frequencies. And these dark bands tell us what the temperature of the star is, what it's made up of. These are many of these are produced by metal, what we call metal lines, but they're iron lines, calcium lines, and they're essentially telling us what the composition is at the solar surface, so what chemicals are at the solar surface, at its photosphere. Now, using this information that we have, which tell these spectral signatures that we get, these unique fingerprints that we get, or the barcode that we get for a particular star, and the Doppler effect, we can do something really cool. So the Doppler effect, just to remind you really quickly, is that if you imagine a fire engine with a siren on coming towards you, it will sound more high-pitched as it approaches you. And that's because sound travels as a wave, and as it's approaching you, that wave's getting squeezed, and so you're hearing things at a higher frequency than when it goes past you and it's moving away from you. And the frequency gets stretched out, it becomes lower frequency, and so therefore it sounds like a lower pitch. And you see that effect also in stars. Then you can see this in spectral lines. So the sun spectra are very thin. These barcodes that you get are usually very, very slim. And they are slim because the sun does not, it rotates in 27 days. It's, as I said, for many of us stellar astronomers, we consider it kind of a boring star. And, but if we look at a much more rapidly rotating star, then the barcode that we get, this very small signature that we get from iron lines and calcium lines, actually gets stretched out. And it gets stretched out because of the Doppler effect. So because it's rotating, the star is rotating very, very rapidly. It might actually spin around its axis in about 6 hours. I've looked at a star like that before, a very young star, like the sun, but much, much younger and rotating like a spinning top. And the reason that its spectral line gets stretched out is because the approaching limb has a higher frequency. So it basically has, its line is basically stretched to lower wavelengths compared to its center. And the bit that's going away from you, the limb that's going away from you, so you're looking at your star from the top in this image here, is stretched out. And that means that the line that you get essentially gets spread. And so, so in fact, the area in that line is exactly the same in both stars because it's the same temperature, but this line is broader. So you can have two stars that are exactly the same temperature, but just because it's rotating, its spectral lines will look different. They'll look broader. Now, this property of broadening out the spectral lines actually allows us to get a lot of information about this stellar surface. And using techniques that are based on same principles that we do medical imaging, that you can get CT scans and things like that, can be used to actually map the surfaces of stars, which otherwise, even with our most powerful telescopes, would just look like pinpricks. They just look like pinpoints of light. This is a really neat technique, and it absolutely just exploits the fact that we know about the Doppler effect. The Doppler effect is an extremely useful effect for a lot of astronomy these days. It's also how we detect many of our planets, and certainly how we determine planet masses. Now, using data that we get, spectra that we get of rapidly rotating stars over a long enough period of time, we can actually derive these very detailed maps of their stellar magnetic fields. And this is the map that we obtained for, let me just scroll back to this star, that we obtained for this star in this period here. So in this period here, we know what its surface looked like using this really neat technique. And the blue and red represent the strong magnetic field at the surface of the star. You can see that it ranges in scale between 24 and minus 24 Gauss, which is a measure of magnetic fields. Now, if you were to see the sun on the same scale, you'd actually get hardly any field detections at all. And the reason for that is the sun has much weaker magnetic field, but also it's concentrated in very, very small regions. And you can see here an image taken of the sun when it's actually quite active. And the black and white regions are like the blue and red regions, but actually the sizes of the magnetic fields are a lot weaker. So these stars that we're looking at, these younger suns that we're looking at, are intensely magnetic. And that has really important consequences for the planets that exist around them. So this particular system that we've been looking at for a number of years, it's called Oudmaijer, and apparently it's the planet that's been found around it is, or at least that star is meant to be host to the planet that the very old now computer game called Halo apparently was developed for. So Oudmaijer is an extremely magnetic star. And what we can do with this data that we're getting, with this information that we're getting, is actually to work out what the environment is like in the planet that is orbiting it. So we know it has a Jupiter mass planet. It has a Jupiter orbiting at the distance of the Earth from the sun, at the equivalent distance of the Earth from the sun. And we can start to model what the environment, the interaction environment looks like. And that's kind of what's shown here in this really beautiful model developed by a brilliant colleague of mine, Julian Alvarado Gomez. And so this is the star itself. These regions here show where you would expect water to be able to exist in a planet orbiting around it. And we know that, like I said, there's a Jupiter mass planet around it. We don't expect the Jupiter mass planet to necessarily host life. But what we can look at is what that interaction environment should look like around that star with its with the planet that is hosting. The other thing is, using our knowledge of the activity of the star, we can actually begin to model and filter out the noise from the star, which is what we need to do to find lower mass planets, because we want to get down to Earth-sized planets, and that is a perennial challenge. And then the other interesting aspect of looking for what the environment is around other worlds is looking for worlds as they're literally just forming. And here what you see is a movie taken, again, with X-ray eyes of a star-forming region, looking at the star-forming region over a period of 10 days. And the brightenings and the dimmings that you saw are massive flaring events that we're seeing on these young solar-type stars that are only a few million years old. These stars are so young, and I know a few million years old sounds old, but again, it's very young in the life of a solar mass star. In these systems, these X-ray flares that we're detecting, the flares that we're detecting at X-ray wavelengths, indicate the release of these huge energetic explosions that, again, are easily 100 to even 1,000 times greater than what we see on the sun, even when it's at its most active. And that has really important repercussions for any planets that are forming around them. So we know that at the same time, at about a few million years old, the planets that are formed, that there are actively planets forming around them. They possess these huge, large disks in which the star itself also formed, and it's out of those disks that planets form. And we've been getting new data over the last few years from this wonderful facility called ALMA, also in Chile. And it's given us insights into what the environments look like around these very, very young stars. And here you can see what are what we think are planet-forming disks. There are stars, and there are very young stars in the center of every single one of these images. These were taken using millimeter wavelength observations, so radio observations, looking at the cold universe. And what's been really surprising to us is that in these really young systems, you can see these clear gaps that have been carved out in these huge disks of material that surround these very young stars. And what that tells us is that it's likely that either there's already planets that have formed in these disks, or that they're actively forming planets, because you kind of need material to accumulate in order to be able to form your planet. And you can see that around these different systems, there are huge differences in the kinds of gaps that have cleared up around them. This line, incidentally, represents the distance between, it's about 5 astronomical units. So it's kind of the distance between, 10 astronomical units. So it's the distance between the sun and I believe Saturn. And so these are huge disks. They are bigger than our own solar system, mostly. But they are all forming planets, we think, at a much faster rate. Now, these are indirect observations that indicate that planets are likely forming, but there are other explanations as well. It could also be that this is due to just the movement of gas and dust. And so we have an upcoming mission coming up that will be looking at that in a lot more detail. And And so these observations essentially combine the, these observations were taken using the ALMA observatory, which is ground-based. It's this massive array of millimeter wavelength telescopes. And in the very near future, we hope next year, we'll have the launch of the James Webb Space Telescope. And that will be allowing us to see these same disks in different wavelengths and different frequencies. And that will allow us to understand what's going on in these systems in a lot more detail. At the same time, we're also studying the energetic environment and the X-ray environment of these of the stars that are in the middle of these disks, and we're trying to understand how this really intense X-ray environment. Let's see if we can get moving on again. It refuses to run. So and with these very strong X-ray flares that they produce by studying their magnetic fields and how they're interacting with their disks, we might be able to understand how these disks come to be the way that they are. And that essentially is me coming more or less to the end of my talk, although I've got a couple of more slides that I'd like to talk about. So in summary, there are some key points to take away here, I believe. The Earth's magnetic field protects us from solar storms. An aspect I didn't cover is that actually the Earth's magnetic field is fairly rare in terms of rocky planets in our own solar system. So Venus is a very similar size to Earth, but actually does not possess a strong magnetic field that can protect its atmosphere in the same way that Earth's does. Mercury has possibly a similarly similar type of magnetic field, but we're studying that. We're actually got a couple of missions going to study that in much more detail. But we don't really understand why the Earth has such a strong magnetic field, and several of the other what we call terrestrial planets or the inner planets in our solar system don't. The sun has very intense storms every 11 years. And mostly this is not a problem for us. Mostly they just cause us to have beautiful northern lights or worry. And that's not really an issue, but we do, especially operating space-based facilities, we do have to watch out for those. And there's a lot of effort going on currently, also at the European Space Agency, predicting when these storms happen and trying to model them and trying to work out how we can robustly predict when they're going to happen and how they're going to affect us, because we need to prepare, especially as in an age when we've got so many more satellites orbiting. Now, other stars reveal whether our sun is typical, and they can also help us probe our own history, not only of the sun itself, but also of the solar system. We found that other stars have these kind of magnetic cycles that are similar to the sun's, but they can have very, very different durations. We know these hugely energetic flares occur on the sun, possibly every 2,000 or 3,000 years. But the big question that we actually don't have an answer to, and there's a lot of effort being spent on that right now, is trying to understand whether the sun is really a typical star. And we're at an age where we can look at millions of stars essentially together. So we're really coming to a point where we can begin to answer those questions. One of the things that we don't know is whether these mega flares that we're detecting on these stars, whether they will cause the same kind of problems for the planets around them that the sun did in the Carrington event way back in 1859. Now, we have discovered almost 4,500 planets. I calculated for the last 20 years, on average, we're discovering a new planet every other day around other stars. But the planets that we found, at least so far, are very, very different from our own. And the hunt for finding an Earth twin is still on. And we think we have some candidates, but there's a lot of work still happening in that area. We know that there's a lot of evidence now, there's an increasing amount of evidence from many different sources that suggest that planets can form while their host stars are still forming. And that's unexpected that it's happening at such a fast rate. And there's a lot of work to understand how planets can form so efficiently, because that was something that wasn't that expected not so long ago. Very young stars are, to use a non-scientific term, extremely, insanely magnetic. And there's a lot of work happening right now on trying to understand what effect that has on the planets that are forming around them. Now, going back to the point that I made up here, that if these other stars have these really insane flares, and if they're so magnetically active compared to our sun, what is the impact of these storms that are happening on these stars on the planets around them? Now we can actually begin to model that using the kinds of maps that we're getting of the surfaces of the stars that I showed you earlier. And here you can see models that we're developing based on the magnetic fields that we get for the star, and work out how it would interact with a planet that's embedded in its environment. And that's kind of what's shown here. And you can see that when it tries to eject material, actually its magnetic field of the star is so strong that it actually traps the material, and it won't allow it to be ejected. And so that is that's something that we really need to understand a lot better. So scaling up the sun and understanding how much more magnetic stars look like compared to our sun is something that we're really trying to understand. And one last thought. So around the very young stars that we've been looking at, this is an artist's impression. This is an image produced by Mark Garlick, and also the team at ESO. And it shows a star, a very, very young star, that still has a planet-forming disk around it, and has a planet that's formed and cleared out one of these gaps. And that's what we think we're seeing in those beautiful ALMA images I showed you earlier. And meanwhile, the star itself has this insane magnetic field. A big unknown that we currently have is what the magnetic fields of planets look like themselves. As I said, we know about the Earth's magnetic field. Jupiter has a magnetic field, but we don't know what the magnetic fields of these planets that we're discovering look like. Our best chance of understanding that in the near future will be to get radio observations. And there's a huge effort, which the UK is also very involved in, called the Square Kilometre Array, which should be able to get down to the kind of sensitivities that we need to begin seeing the kind of interactions between star and planet magnetic fields. So we're entering a really exciting age to understand the environments around stars like the sun, but that are possibly a bit crazier than the sun. So thank you very much for your time. And I think that's the end of my talk, but I'll be happy to take your questions.
Thank you so much, Gaitee. We really appreciate that. If you could stop sharing your slides, then we'd be able to chat and have a nice little break. We've had some fantastic questions come through, hot and fast, so I hope you're ready if that's okay. The first one I'd like to share with you, so it's from an anonymous attendee. Oh, I forgot to introduce myself. Hey everyone, I'm Erin. I'm the Physics Outreach Officer here at the University of Leeds. I was just really excited to start asking questions. Sorry about that, but we're back to the questions now. So Anonymous asked, how does the solar cycle influence our climate?
Very good question. And this is an area that's been a hot debate for a long time, and particularly in the context of climate change. So we know that when the sun goes through extremes of activity, it can affect our climate. So way back in the early 1700s, there was a period of about, I think it's 50 years, where the sun essentially had no sunspots, didn't seem to have any flares, and was almost not active at all. And that period coincided with, at least in the northern hemisphere on Earth, with what we consider what we call a mini ice age, basically. So the Thames froze over, things were very cold, and that continued. Now, there may be other reasons for that. So there's a lot of debate about whether it was just the sun that was impacting that. Apparently there was a lot of volcanic activity as well, which might have also affected it. So there is a lot of debate about it. What there isn't much debate about anymore is whether the rate of climate change we're seeing now is at all related to changes in the sun. And that's because we have solar data going back ages, and we have data on Earth that actually track solar changes over centuries. And the rate of change that we're seeing now, there's nothing else that we can use to explain that other than us, essentially, man-made causes of emissions. So, and that is the consensus amongst all the solar physicists I have been privileged to talk to in my career.
Thank you. Okay, so we have a question from Daniel, which I thought was pretty interesting. So Daniel asks, is our solar system non-typical when compared to other systems? It seems to be far more common to have larger gas giant type planets closer to stars over having them farther out like our system. Is this just because it's easier for us to detect this, or is it generally thought to be more common to have star systems like this?
So so essentially, it's easier to detect planets that are closer in. I mean, I guess the big surprise has been that there's such a diversity of planetary systems out there. We didn't really expect it, because we really thought we understood how the solar system worked, and that's how everything should work. And that clearly is not the case. So we need to understand disks a lot better. But actually, in actual fact, close-in Jupiters or Jupiter mass planets are not that common. In fact, it's much, much more common to find lower mass planets. It's just much harder to find them. But based on the best statistics we can derive at the moment, it's actually not more common that you have close-in Jupiters. What is true though, and what appears to be the case though, is if you do have a close-in Jupiter, it's very unlikely that you'll have a lower mass planet further out. And that may be because it essentially just cleared up a lot of material or even ejected smaller bodies outside of that orbiting system. So we may have free-floating planets, but they certainly don't seem to survive if there's a close-in Jupiter for very long.
Cool. Okay, so I'm going to go to Andy's question. So Andy asked two in a row, and I kind of just like them both, so I'm going to ask both of them. So, so the first part is, what is the physical process that causes the cycle of the sun to be 11 years? So this is something that I was wondering too. Why is it 11 years? And the second question was, if you personally could closely observe any star in the universe, i.e. from an orbiter, which one and why?
Oh, wow. Good questions. Okay, so 11 years, I mean, I wish I knew the answer to that. I mean, the whole reason that we have Solar Orbiter is because we think it's what's happening at the poles of the sun. And weirdly, we don't really know what's happening at the poles of the sun. I mean, we've had a couple of missions that have flown over the poles, but what's really cool about Solar Orbiter is it's going to keep going back to the sun at higher and higher latitudes. So it's going to be getting closer and closer to the pole and getting this view of the pole as the solar cycle increases. So we're coming out of a minimum right now, and the solar cycle is going to be increasing. And so that is one of the major things that Solar Orbiter is going to be trying to answer. So we think it's to do with circulation from like the north-south direction, setting the length of these cycles. But to be honest, we don't have the answer. And that's one of the major reasons why we're still running these missions, because we literally don't know. And also the sun it has this 11-year cycle that we all know and love, and that's great. But it also has much longer cycles as well. I mean, the Maunder minimum may be one example of that. And we just don't have them that well characterized. But there is lots of stuff happening in the sun. And we know it's to do with the internal flows of the sun. So we know the sun has a lot of convective flows, and there's a lot of different surface flows that are happening that allow the magnetic field inside it to get twisted up and change its direction. And that allows it to just keep regenerating magnetic field and it not dissipating over time. And oh, sorry, the second question about which star would I like to go around?
Yeah.
I mean, that's a really good question. So, I mean, do I just have to choose one?
For it, putting you on the spot.
There are so many. I mean, I would really like to study the really low mass stars. So the most common stars in our galaxy and in our universe are very low mass stars, much lower mass than the sun. M stars, we call them. So the sun is a G-type star. And so I would love to know what happens in M-type stars. And those we don't really understand at all, because they stay weirdly active for billions of years, and we don't really understand why. So I would love to really have a mission that would look at M star, an M star in insane amounts of detail.
Cool. Okay, so we're probably getting to our final questions, and I apologize for everyone for not being able to answer all of them. We have a question from Thomas asking, just saying that the transit method was so groundbreaking in discovering new planets. So what makes it so much more effective at finding these exoplanets compared to all of the other methods?
The transit method.
Yeah.
Yeah. So it's, in some ways, it's because it's a relatively easy detection. I mean, it's looking at, you can get images of many stars in one shot, and you can look at their brightnesses. What's really hard to get is the kind of precision that we needed to get to be able to really get the numbers of planets that we needed. And that's really why we wanted to go to space, because the Earth's atmosphere mucks up a lot of things. So certainly these massive wide field detectors that can look at huge fields of stars all at the same time makes it a super efficient technique to look for that. The thing with transit method, though, is you actually need backup methods to work out what you've actually found, because there are many things that can cause the light from the star to be blocked, and activity is one of them, for instance. So then you need backup observations looking at radio velocity signatures to just confirm how big that planet might be, whether it's there, and follow that up. And the really cool thing about the transit method is that it's just really efficient. It's very efficient. But like I said, like we have a massive mission coming up in a few years, Plato, which is going to look for much lower mass planets, which will be super exciting. But it needs ground-based support. We need a lot of spectroscopy looking at individual stars at extremely high precision just to follow up and confirm the planets that have been found.
Wonderful. I think that's a great place to end it. Thank you so much, Gaitee, for answering all of our questions. If you still have questions, or maybe you submitted them and they weren't answered, please, I'm going to plug your Twitter. Please tweet Gaitee. Her handle is @onlygaitee. And so I'm sure she'll be able to answer questions that come through on Twitter. So please get in touch with her there. This lecture was recorded, and we're going to share it and upload it to YouTube. And we have all of your emails if you joined with us today. So you'll get a follow-up email with the link to that if you'd like to share the lecture further. We'd love for that to happen. And after we close the lecture, the webinar, you'll just get a little survey, which is basically just an opportunity to let us know what you thought of it, and what we can do to plan for the Bolton lecture next year. We'd love for you guys all to join us again as well. Hopefully it'll be in person, but also live streamed. And so I'd just like to say thanks to Gaitee again. She looks like this way on my screen, but I don't know if that's the right way. So Gaitee. So thank you so much, Gaitee, for joining us tonight. And thank you so much for joining us here at the University of Leeds. I'll say a nice goodbye from the School of Physics and Astronomy. Gaitee, you're welcome to wave goodbye as well.
Thank you, Erin. Thank you, everyone, for joining. Good night from the Netherlands.
See you guys later.